Okay, this is picking up from the second video. I'm trying to re-record, so I may have to define variables as I go, but I think I've got everything I need. So if I want to group my data, I can use the group by command, and male is the name of the column header that I want to group by. So remember, male has zeros and ones in it. And now I can make a histogram on the exposure column of my grouped data. Okay, and then you can see that. I guess it's not telling me which one is male and female. I don't know why, but I'm sure there's little, you can Google that and find out how to put those labels on. Okay. If you want to create subgroups, which we do often, we can use the get group I put the underscore in the wrong place. Sorry. So what I'm going to do is I'm just going to make these shortcuts for myself so I don't have to type out get group again. So what's the data type of grouped? And data type for G0. So even though the grouped is a group by structure, the type G0 and the type G1 we're both back to data frames again. It's sometimes useful to know what it is that you're looking at in terms of data type. Okay. You can look now at data, for example, standard deviation of the whole set, or you could do the same thing by group. Since both are data frames, you can just do this for each subgroup. And that's what I'm encouraging you to do for your homework, is that once you have your groups, when I say do such and such by group, what I mean is now that you've got your 4 groups, so for you it'll be 4 groups, run the same command 4 different times now that you have grouped data. Okay, and then you can look at the size of the data. You can do this for any data structure. Okay, the shape gives you more information. Okay. If you just want the height of the data frame, you could just look at the first element of your shape. Okay. We can do scatter plots by subgroups. And for example, I might want to use symbols. And we will do our standard dots that we always do. We'll do those later. But if I just want something quick and easy, I can just use the symbol, and then I can put them together like that. Now I'm going to create lines that fit actually any polynomial. A polynomial of any order, but we're just going to use lines. So it's going to make life easier. We've seen this before where normally we would have to create a whole array. I think we did that in MATLAB. We've done so many languages I don't remember which is which anymore. Okay. But I spelled it wrong, so that makes a difference. It's always good to read your error messages. A lot of times you can save yourself a lot of effort by just reading your error messages. There we go. We got ourselves 2 lines. So what does this do? In the NumPy package, we have a polynomial fit command, and what we're doing is we're looking at all the X data. So what does this look like? That is what we're looking at. And so the Y is the G1 exposure data. Okay, so that's what we're doing. We're taking these guys and merging them together to come up with a best fit line. If we put degree equals 2 at the end of that command, this command here, then we'll be getting a parabola. Now, as a little aside, if we decided to use a parabolic fit, we'd need the arange command. And let me just show you that. So the arange command allows you to go, for example, from 10 to 30, stepping by 5, up until but not including the 30. If you want to include the 30, then just go beyond the 30, be it ever so slightly, and it will just calculate it differently. See, everything's turned into a floating point type now. But instead of having an integer type, it's going floating point, and it allows you to go up to 30 because it's smaller than 30.0001, so it includes it. So those little tricks, but you'd really do something like maybe go from, let's see, from like 0 to 2 pi, like something like that, by 0.1, and then you get a whole mess of points. But that would be better for plotting something curvy. Not enough points for you? Well, if it's still too crunchy, then you just increase the number of points. Okay, so since we're only plotting a straight line, we only need the 2 endpoints, and adding additional points is just extra work for the computer that doesn't buy us anything in terms of accuracy. So we're not going to do it. We're not going to pull this stunt, so we're not going to do that here. Okay, so now we go on to creating our polynomial, which again is just very simple because it's just a straight line. And it's a one-dimensional polynomial, and we shove in z0. And remember, what was z0? Z0 says it's an array, and the very small array, these are, this is actually telling you the slope of the line and the intercept of the line. If this had been a cubic, you would have 4 points in there, 4 coefficients for your polynomial. And so we're just going to do the same thing for the other line. And so what did we get here? We got a polynomial. We took an array and we turned it into a polynomial. We're just passing these coefficients around the different data types. So we had spit out the coefficients of the data type, and now we are feeding them into a structure called poly1D. And that poly1D is able to create points for us. So I'm going to create a column called line 0 in my data structure. So there's going to be a new column, and we're going to compute it using P0 on my data. And we're going to do the same thing here. So we're going to have 2 columns now. And now you can see we have, by just looking at the data types, we can see we have 2 new lines. Let's look at this again. What did we do? What if we had, well, what is P0 of 5? We just get at an individual point. P0 of 0, 10, 20, and we get out these results. Let's stick the 5 in there so you can see what's happening. Okay, so if we just evaluate it at 1 point, we're just going to get the result of that interpolating line at that 1 point, and here it is. But if we wanted it at 4 points, that's what we'd get. And if we wanted it at 100 points, we just shove the array, and so here's where you'd use arange. You'd shove it in there, and then you'd get out a whole bunch of y values for the input x values. Okay? So hopefully that makes sense. You have no need to use the quadratics on the homework, but if you decide you want to use it on your project, I wanted you to know how you would do that. Okay, so how do I plot the points and the lines together? I'm going to pause this while I type this in. Okay, so these 3 commands are determining, first it's creating our 2 lines, and then it's going to create the 2 sets of points. It's the same points we've been plotting and the same lines we've been plotting. So you should recognize what it is I'm trying to do here. And now I'm going to show the plot. Again, there's opportunity for putting titles and all sorts of stuff. In fact, I'm going to do all this again with slightly different arguments. Okay, so these are the same 4 commands basically, but I just stuck labels on the women and men And then I also said legend, women and men. And so since the software knows that this label was on this red line and this label was on the blue line, I mean, I could have put the labels on the red dots and the blue dots, but I put them on the red line and the blue line. Okay, so then it will know to make a legend, location equals 2 means the upper left corner. Heaven only knows why that is what that is, but that's okay. If you want location 2, then that's what you do. And since it knew where the labels were, it decided to put the symbol for that structure goes up in the legend. Okay? So there you go. And moving right along, if we want to compute correlations, there's a couple ways to do that. So I wanted to show you that these different packages, they have different ways of doing these things. And they take different data structures and they have different syntax. But if you just want a straight up correlation between two columns, you can just take one column dot CORR and then the other column. And of course, now that we have G0 and G1, we can just say, hey, if that's what you do on a data structure, I have other data structures with the same fields. I can just swap out a data structure for another similar data structure. And again, when I say split by data structure, this is what I mean. Just go like that. And you can also pull out the data, for example. I'm going to pull out this column. And I'm going to actually turn it into a list. So for example, type of expo is a list. What's expo look like? It's just that column, but I've turned it into a list. Okay, so I could have just said C exposure. I'm sorry. Why did I do that? Something like this. I want to know what is this data type when I pull a column out. And if, well, I guess it turns into a series. Nice to know. But now I want to look if I just have a list. And then I'm going to create another list. So I have two lists. And I can just use a NumPy correlation coefficient for these guys. Now we actually have a correlation matrix, but we're only trying to correlate two things. So we can just do like that and say, hey, I just want one of the corners, either index 0, 1 or 1, 0. It's the same thing. And it would just tell you that correlation, and we noticed that it was the same as the other one. Okay, so I tried to just pull this command, but I obviously didn't go back far enough. So this is the right structure of the command. There we go. So you see the correlation coefficient that we got from the NumPy package is the same as we got over here. I don't even know what package gave us this. Anyway, they're the same. Okay, box plots are cool, and box plots go well with ANOVA, but I didn't talk about box plots in the ANOVA section of this lab because I'm already talking about it here. And honestly, I don't really know what that error message is about, but there you go. And if you want to group by male or by anything, I can say, I guess it goes over here, group by, and I could group by, it's male in the lab. I'm just going to group by age. Okay, so it's saying here that you don't know what this is, but this is the college age students. Group 1 and 2 is middle age, and 3 is older. But you know what, were not that many people in this sample. There were a decent number of people in the sample for 1 and 2, and 3 was kind of sparse. But I don't think that 2 and 3 were significantly different. But the college students tend to expose themselves more, and I think there's a couple reasons for that. And one is simply they're on campus, and a lot of them live on campus. It's a lot easier to dress for the weather when you're at where you live. But I mean, you know that there's fashion reasons as well. But anyway, that's that. Okay, now we want to recode the variables. All right, I'm going to create a new column, and it's all entirely male. So let's take a peek at the data, and we can't see all of it, but it scrolled by really fast. We've created a new column, and it's all male. And what I'm going to do now is I'm going to go back and pull anything that needs to be female and make it female. So it's going to be a sneaky double loop that looks like a single loop. And in your homework, you have 4 groups. I have just 2 here, so I only need to fix one group to be female. In your case, you should preset the first group to be whatever you want, and then you have to overwrite 3 more groups instead of just 1 more group. But the structure should be the same. For index, comma, row in my data iter rows. This is the sneaky part that I'm not going to fully explain because it's a Python structure, but you just have to match up the pieces and it'll work. Okay, so I'm specifically using a structure that's inefficient so that you can perfectly copy my style, so that this is more generalizable. Okay, so normally I would do it slightly differently. Okay, and so let me explain what this is saying. So for every index, that means we're going from the top of the data set all the way down to 502, and for every row in the data set, so for every row and column, so now I'm looking over the rows, if in that row I see that male is 0, okay, so for if the male is 0 in that row, then and you've seen this command before, I'm going to change the contents in that same index, whatever index I'm in, so whatever row I'm in, I'm going to change the gender column to say female. And this is a little inefficient because I could have just said if row male, if not row male. Because if row male is 0, it's the same as Boolean false. So that's what I would have done. I would have used an if, and you can put an else here, or an else if, but I want you to be able to copy this easily. And so this is the easiest structure to just copy. And so now I can just quickly look at my data and say, aha, it's correctly, well, I think it's correctly, it's written females over top of some of them, and so I think it's done it correctly. Okay, so now I'm going to make the same box plot I did before, but now I can group by gender instead of male. Okay. I must not have spelled something correctly. It should be in quotes. There we go. So this is exactly the same plot we had, but now we have better labels. That's opposed to, you know, like you could also have just done, there was one where we didn't group by anything. Anyway, you could have just, since we have G1 and G0, you could have just made separate box plots like that. So you could have done G0 box plot column equals exposure and done it that way, and then that will be acceptable as well. Okay. Now, if you want to do a t-test, you have to get it from this package. So we have to do yet another import. Well, where have we seen this before? The nice part about this is that everything you might want is freely available, but the annoying part is you have to keep installing stuff on your computer. All right, so I'm going to make up 2 different categories. And And I'm going to make up another category. So what is the type of this? It's a data frame. And this is a data frame. So do they look different? And that's cat1 and G0. Oh well, cat1, let's say shape, and G0 shape. G1 shape. Okay, they are not identical. Right. Okay, so I had forgotten that I had created G1 and G0. I had just created these before I did all those extra columns. So that's why we have the extra columns. So I created the line 0, line 1. So we want to do... Okay, so if I look at my data D types, G0 D types, notice that they're not really the same. Right, so we have all the way up to sunny time umbrella wind, sunny time umbrella wind, but then we have, anyway, these guys are new. These guys are 3 new columns we have in the M data types. And so now we have these structures. We have new, well, this isn't very helpful. Okay, but we have hold on, let me grab that command for a second. That was the command I was looking for. The describe command shows you a lot of your data, but if I look at cat1 or cat0, you see that's slightly different. Well, that's lovely. I meant cat1. There we go. Anyway, you'll see they're different because we did them at different times. That's why they're different. But anyway, we have more than one way of partitioning off our data so that it's in 2 groups. So now we can go ahead and do our t-test. And right here is a test statistic that I could not care less about, but this is my p-value. And it turns the test statistic into a p-value. This kind of means -4 means the difference. I think it's just your z-score, but it's not a z-score, it's a t-score. So the reason I don't care about it is the p-value gives me much more concrete information. It says it's really, really unlikely to happen. Okay, so you can see if we stick in G0 and G1 instead of cat1 and cat2, we get exactly the same results because we have those columns are the same. G0 and G1 are the same as cat1 and cat2, except that cat1 and cat2 were made at a later time and therefore have more columns. Okay, so that's fine. Hopefully that's not too confusing, but we do have different ways of accomplishing the same thing in Python. Okay. Now we're moving right along to drawing a normally distributed sample, and we're going to do this by tacking on yet another column onto my data structure. And it's going to have a center of 100, a standard deviation of 15, and the size of it is going to be the height of our data frame. So that's how we're getting that. And then we're just going to yank this back off. And we didn't technically have to attach it, but whatever. Okay. So now I'm going to actually give this a title. Your histogram title. Okay, so we're going to go ahead and do a show on this. Yay! And it's sky blue, it's transparent, all this stuff. Great. Okay, and there's a couple things that of course I always ask you for, like pie charts. It would help if I could type. And we're going to show this. And it's kind of ugly, but you can reshape this. There's all sorts of different things you could do with that. Okay, and creating confidence intervals. This is a major pain. Okay, so I looked around and I couldn't find any better way of doing this. Every single instruction manual said you had to do it by hand, which seems really stupid. So maybe I should write a package. It seems odd that nobody wrote a package, so somebody must have, but it's probably just not one of the main packages. So we've already imported SciPy, but to just make things a little easier, we're going to import the stats subdirectory, and within the stats subdirectory we're also going to import SEM, which is standard error and the mean. Okay, and so we're just going to take the mean. Let's just say exposure. We already have expo, so M is the mean of expo. I mean, it's really weird that we need a package to get mean in Python. That's kind of pathetic, but it is what it is. And the standard error of the mean for this data set, there we go. And then N is the length of the data set. We actually don't need that, but this is kind of pathetic that if we want the length of the data set, we do it that way. Okay. Now, we're going to do, first of all, before I glue this together, I have to tell you what we have access to. This is similar to our tables that we're used to, our Z tables and T tables. However, it's backwards, so we have to do the reverse lookup. If it's looking up to see, okay, at what Z value do we get half the data to the left of the curve? And then that would be at 0. And then think about this. Let me draw you a picture for this. If you have a curve, and we know the 68, 95, 99.7 rule, let's just cut this in half, okay? So we have, in this case, 34 over here, and then 50% over here, right? So we should have about 84% to the left of this line, which is at the 1, Z equals 1, right? So so if we wanted to figure that out more accurately, we would do the 0.84 thing and say hopefully it's close to 1, and it is. So that's what it's telling us. And so if we need to find, you know, a 95% confidence interval, what's the cutoff for that? So we want to know, it's going to be really close to 2, super close to 2, but let's be more accurate. So what is half, like the tail is going to be 2.5%. So we're going to ask the same question, but we're going to say, what if we're just cutting off 0.025, but that's going to give us the -1. See, it's close to -2. And what if we want to do the right-hand side? We're cutting off all but 0.25. So here's the magic number that you probably know from stats 202 or stats 601 or whatever stats you took, that tells you, hey, if you're going to do a 95% confidence level, you're going to multiply by approximately 2 on either side, but you're going to use that. So let's go ahead and save that. However, we really prefer a t-test. So what would we do for a t-test? We want the cutoff. There's a different command instead of norm. It's called hold on a second. But we really want T PPF, and when we want to put in here n-1, where n was the length of the exposure thing, there we go. And so it's very, very slightly different from what we had up here because we have such a large data set that our cutoff is going to be very similar if it's a t value or a z value. Okay, but it's better to use the t value. And so then what we're going to do is say h is is standard error of the mean that we calculated, right? So h is going to be standard error of the mean, and then it's going to be plus or minus, well, times the cutoff. So that's what our cutoff is going to look like, and so my interval is going to be something like h minus m, sorry, m minus h and m plus h. So that's a lot of work, but that's what we get. And we have our interval. Okay, just a couple more things. ANOVA is painless enough. We have enough stuff going on here. So we're going to use F and P to hold the results of our ANOVA calculations. I'm going to see how different males and females are in exposure, and I don't really care about F. That's my F statistic, but P is the p-value, and that's the one I care about. It's very, very small, so I can conclude that this is a significant difference. Chi-square is not so bad because we have already imported SciPy, so I'm going to just import directly one more thing, chi-squared contingency. There's also a regular chi-square, but we're not going to use that. We're going to use a crosstab first, and I'm going to show you what it looks like, and then I'll feed it in. I'm just doing this because I can. Okay, so I just happen to have the data split by gender and by age, and it's completely meaningless. We have more females on campus, but for the faculty, we have more males. And then for the older people, you can see we only have 16 people who were older than middle age, and so they could have just been combined in with the middle-aged people. Wouldn't have made much of a difference. It would have balanced out the male-female ratio a tiny bit, but for whatever reason, we have way more females from the student population, but from the faculty population, it reverses, it looks like. But that was just a very, maybe it was a small sample, I don't know. I don't know if that's accurate, or maybe the males on campus tend to wander around more, I don't know. If I wanted to include the margins, I can just say margins is equal to true, and it'll do the summations on either side. But I'm not going to use that for this example. Okay, I'm going to just save out my crosstabs in a separate structure, and I'm going to just, so that's still a data frame, that's nice. Okay, and so I'm going to feed this into my chi-squared contingency, yay, tab complete, and I get this mess back out. And the only thing I actually care about is this guy, which is my p-value. So again, the 11.58 is some kind of chi-squared result that I don't really care about. This guy is my p-value, which I care about. And this thing that gets sent back here is my expected value matrix. So I get all that stuff back, and if all I care about is this guy, well, I could have just said, what is that? There we go. There's my p-value, and that is all I need to show you for today. Hope you got all that.